Welcome, global supply chainers, to our third live event of SC0x. Thank you very much for joining today. My name is Alex Rothkopf. I'm your course lead, and I have invited today Chris Kaplis, who's the executive director of the CTL and also your teacher in the past weeks. You have spent a lot of time with him. Thank you very much for joining, Chris.
No, glad to be here. Glad to be here. I bet you guys are glad to almost be over.
Yeah, we have only the final exam
Exactly.
and our live event today. I think students are looking forward to that. So as usual, we have set up our Slido account. You can log in at sli.do, put in the event code, hashtag SC0x-3, and you will have this live feed and the opportunity to interact with us in two ways. On the one hand, you can put up questions to us, and we will pick these questions as we see them fit to our content that we are going to do today. And on the other hand, we are going to put out some polls. And I'm running one poll right now about the contents that we have served you with in the last 11 weeks. And
Before you switch though, so for questions, put in a question, but also we're relying on you guys to upvote the ones that you want to listen to. So if you see a question in there that you like, then upvote it. That way we'll know which ones are the most interest to you all.
Yeah, absolutely. That's important to us because then we can see that easy.
Prioritize.
Yes.
It's like a heuristic.
So our agenda for today is the welcome, which we just did. And then Chris will do a recap of what we've learned so far and an outlook of how what we've learned in SC0x ties to all the other courses that are upcoming, SC1x, SC2x, SC3x, and SC4x, to make the connections clear and why we have set up the program the way it is. Afterwards, we have a couple of problems from practice that further should connect what we've done in the course with all the with different problems that you can come up with in transportation and logistics, let's say it that way. We're going to go through them step by step, discuss how we apply our methods, and see if you have any other questions. You just put in on Slido. So Chris, I will turn it over to you to discuss with us some the learnings that we had.
Great. So I hope you guys enjoyed this course. It's the first course that many people take when they go into the MicroMasters or the SC0x sequence, but it was actually the fourth class that we created. It was one of the last ones. And the reason why we did it is we found that just like when you come to grad school, you usually want to get all your math up front because then you're going to have all the tools in your tool belt to be able to solve things as you go forward. And that's the approach we took here. What we also tried to do was weave in hints, at least, of how these different techniques would be used in both the rest of the courses as well as in your career in supply chain, because every one of them has a very practical use. I didn't do anything theory for theory's sake. Everything is there to give you the underpinnings. So there are four big things that I hope you learned. And I'm not going to go into equations. I just want to do big picture things. The first is, and that we tried to do, is make sure you had a level of mathematical dexterity because it's a model-based course. And 0x, 1x, and 2x are all model-based. Everything you do in supply chain, whether you're explicitly dealing with a model or you're just dealing with the results, is the result of a mathematical model. Network design, procurement, all these things rely on an underlying mathematical formulation of costs, time, some kind of relationships. So I wanted to make sure that you have practice in using functions and using approximations and just getting your hands wet and getting comfortable back with the algebra that you think you didn't need to use again when you learned it in 7th or 8th grade, because you need to have that dexterity. So that's the big takeaway. Hopefully you're getting more comfortable when you see a summation sign. You don't freak out because it's just notation. The second big thing that we did in the first part of the course was optimization. And I took you all the way from unconstrained classic optimization using calculus just a little bit so you understand it's not magic, and then went into constrained. So we did minimum, maximum, first order conditions, and then second order conditions. How do you know you're at the top of a hill, right, in the dark? And the whole idea is because any step you take takes you down. It's the same concept that we used mathematically in our formulations. And then we also went into constrained. This is where we say, okay, you've got an objective function you want to minimize or maximize, but you're subject to certain constraints. And so how do you work with that? And you saw the amazing result with linear programming that when you have a feasible region that's convex, that the solutions are going to be at the corner points, which is an amazing result that hopefully you appreciated, because we rely on that for a lot of problems. In fact, a lot of the stuff, if you go into future grad work, you'll find that a lot of the work is to try to convert a complex, say, mixed integer linear program or something complex into a linear program, because we know how to solve a linear program very quickly. So as you go into practice or into higher grad courses or into other studies, you'll see that the problems you're solving are bigger and bigger and bigger. And hopefully you realize for integer programming or mixed integer programming, the size will kill you. And so there's all these tricks and things you can learn at a higher level, how to convert things into a linear program. But everything we did in optimization, we're trying to come up with an answer. It's all prescriptive. So we did unconstrained optimization, which you will use, and I'll talk about that later in SC0x, constrained optimization, which you'll use a lot, especially mixed integer linear programming. Every supply chain uses this. They might not be explicit about it, but when you're deciding where things flow, where things get located, at the bottom of it, it's a mixed integer linear program. And so hopefully you got a feel for what you can and cannot do with a MILP. The other things that we added in, I say probably 2 runs ago, we added in a section on algorithms and approximations. If any of you are over the age of, say, 55, and I'm sure there's some of you, you might have remembered a slide rule. But the vast majority of students that certainly I see at MIT or they're on this class don't have a slide. Did you ever have a slide rule, Alex?
No, not really. I had one in engineering school just to see how it works, but I never worked with it.
The thing about a slide rule, it's awesome, but it also helps you think about approximations. And so you think of orders of magnitude very clearly. We've lost that skill. I had to use a slide rule my freshman year in high school, but that was it. The calculators came in. So we've lost the skill of approximation. That's why I put that in there and did some approximations and I used the approximation technique to also illustrate algorithms. So some of the algorithms in network optimization that I talked about is shortest path, traveling salesman problem, vehicle routing problem. These are used every day. And so when you have the exact data, you can use exact algorithms or maybe heuristics, those approximations, if it's really big. But sometimes you need to make a decision and you have very little information. And that's where these approximations come in. I gave you one example using where it's approximation of local routing distances, which is very powerful. And I'll explain why in a few minutes how it's used. But everything we did for that first part of the class was mainly deterministic, but it was also prescriptive. These are techniques that'll give you an answer. How many facilities should I have? Where should I put them? Which things should I do to maximize my revenue, minimize my cost? It gives you an answer. In the second half of the course, we went into more descriptive and predictive things that don't tell you an answer, but they either describe a situation or they predict an outcome based on some certain inputs. So we went to probability and statistics. Probably the hardest week there was when we did hypothesis testing. There was a lot of stuff there, but I wanted to make sure you got it all. And so we applied it. So hopefully you took away how to handle distributions. You'll see the normal distribution throughout your career. Poisson distribution as well for if you get into spare parts and slow moving things. And I introduced triangle distribution. Again, a great approximation if you don't have any detailed data. Hopefully you're comfortable with characterizing data. Every project in the 15 years I've been here at MIT, the size of the data sets that students have dealt with to solve research problems has grown by a factor of 100. I mean, it used to be everything could be done in a spreadsheet, right? And now this is why we teach you in SC0x, SQL, and large, massive data skills, because you need to be able to deal with and how to characterize large sets of data. Data cleaning is a critical skill, but being able to characterize data through central tendencies, the dispersion, all of that is a very important skill that hopefully you picked up. Then we went through all the hypothesis testing. What do you do with the data? The idea of p-values, point estimates, confidence intervals. Hopefully you got a handle on that, and the way that you'll get better at that is just doing more problems. And so after a while, you see it's very mechanical. That's why we covered a lot of it. But once you understand the concepts, the mechanics are very straightforward. And so when do you use a normal distribution, a Z statistic versus a T statistic? And hopefully through repetition, you'll get comfortable with that. Finally, we focused in on the last part, regression and simulation. And these are more predictive techniques. They're going to predict what an outcome will be. They will not tell you what the best solution is. There's no such thing as a prescriptive regression model or a prescriptive simulation. They tell you, given these inputs, here's what you expect the output to be. It won't tell you the best. People really get confused over this, but they're two very separate techniques. And they work well together, but they're separate techniques. On regression, I went through example after example of building a model, ordinary least squares. You'll use this if you do any forecasting. It's widely used in practice. There's a lot of other techniques that you can go into, but ordinary least squares, where you have this dependent variable, it's a function of all these independent variables, thinking back to functions. It's used widely in forecasting. I use it in cost analysis. So you'll see that a lot. Simulation is used mainly a lot of times within a factory four walls. I've seen a lot of simulations, or within network design to see how a certain solution or a certain policy will go. And simulations make a ton of sense if the situation is so complicated you can't create a nice closed form analytical solution or can't solve an optimization model. And it's also really good to do what ifs. What if I change my delivery policy so that it's every third day instead of every other day? And if you set up your simulation, you can see how that effect will be. And then at the end of it, you say, is it any better than my previous solution? That's where you use a hypothesis test. So at the end of a simulation or regression, you're using all of those statistical tests to validate the model and to help give you some insights. We also did queuing theory as well in there, and that kind of fits right in with some of that as well.
Mm-hmm. So I asked students which of the concepts they liked most, what was most interesting for them. And it seems to be that your drive for constraint optimization has picked up. There was a picture that we saw also before. More than 2/3 of the answers say, well, we like constraint optimization. Actually, simulation seems to be also very well perceived.
Yeah. So personally, I'm showing my bias because I'm more of, it seems like it's like religion, right? You're one or the other. I tend to be an optimization guy. I cut my teeth on large scale combinatorial optimization. And so that's the biggest tool in my tool belt. I don't know. Are you also more optimization based?
I'm also more optimization based, although I'm also kind of exploring all that big data stuff where we get more into regression analysis, but it's mostly optimization.
But to be fair, I've been using regression on the side for other projects for, gosh, 15 years. Yeah. Simulation has never been my strong suit, but we have some people here who it's a primary tool. Yeah. So as you get up to like a PhD level, you find that you generally you find your methodology and you kind of use that a lot, or you find a domain. But we try to make sure you have at least a taste of everything.
Yeah,
that's good. Yeah. Okay.
So hypothesis testing is still not very much favored.
Hypothesis, it's, you know what? You use it when you got to use it.
Yeah.
It's a way of, so if you're working in a warehouse, you're not going to whip out your hypothesis test that often. But if you're doing an analysis to try to justify spending $5 million on a software system that'll improve operations and increase time, yeah, then you might want to do it to say, hey, you know what? This is a solid improvement, or this is not. So you got to pick when to use your tools.
And we will cover that in our problems on practice a little bit of how we could use hypothesis testing.
Yeah, actually, right? Let me go. Oh, do you have another question? Or?
No, perhaps we go to...
So you had these big things that you learned, and all thing in 8 weeks of content. A lot of stuff was put in there, and I know that. I know I put a lot in there. I did that on purpose. Let me explain how it's going to be used in later courses if you continue on through SC0x to 4x and continue with the MicroMasters, which I hope you do. In SC0x, you're going to learn all about forecasting demand, managing inventory, and planning transportation. It is the core course. It's the first course I created. It mirrors SCM260, which I've been teaching here for more than 15 years at MIT. And it's the classic trade-offs between demand, planning, inventory, and transportation. So having too much and having too little, having a fixed cost and a variable cost. And as soon as you think of that word's trade-off, you should be thinking optimization, because you're finding the best under these certain situations. So in forecasting demand, we'll do a lot of work with functions. You'll You'll use regression. You'll use statistics to understand the accuracy of your forecasts. And it's all one big function, right? So your demand is going to be a function of maybe some different patterns, a level, a trend, or some kind of seasonality. You'll use all of those regression and statistical tools to come up with a better forecast. For managing inventory, you'll use unconstrained optimization. The classic inventory model is called EOQ, economic order quantity. You'll recognize it as that you can solve it with a first order condition, and you'll end up with the EOQ formula. But hopefully by taking SC0x, you know where it came from. It's not a magic formula that someone handed down to you, but you'll see how it came about. You also have a lot of minimum costs under uncertainty. So we'll use a lot of statistics there and distributions. We'll use a lot of the normal distribution and the Poisson, because you want to understand if you have a certain amount of inventory and your demand distribution, which is a stochastic variable, what's the probability I'll stock out? So you use probabilities a lot. And so the idea is you're going to be figuring out how much inventory to stock such that my probability of stocking out, which is the probability the demand is to the right of your level, is at some level, less than 10%, let's say. So we'll spend a lot of time understanding how you set your inventory replenishment levels based on probabilistic demand. And then in transportation, you'll really look at optimization of time versus cost, and you'll see how the uncertainty and variability in transit time affects the amount of inventory you need to hit a certain level of service. And we'll do a lot of mode selection, understanding how variability is. So we'll really focus in. But the big thing for SC0x is you're going to see at the end of the course, it really boils down to one big equation, the total cost equation. And you'll see that forecasting affects the equation in a certain way. Inventory is affected a certain way, and transportation impacts it a certain way. So what you see is how to make the trade-offs of all these different levers that you have in your total cost. So SC0x will use all these models.
Can I add a question that just right fits into that all that inventory discussion? Because Prashant asks, how are we going to cover different inventory models, such as a smooth, lumpy, and erratic intermittent demand too? So these are more special circumstances that we have in inventory management. Do we cover that in SC0x?
Well, that's what Prashant's describing are not really inventory models or demand patterns. So yes, we will. We'll cover Croston's method, which really looks at how, if you have lumpy demand, and when do you have lumpy demand? Let's say if I have a parts replenishment, I give spare parts out to cars, or I might, manufacturers might order from me. I might get an order occasionally, and the order might be of very different sizes. So if I look at just the average, it doesn't make sense because there's a lot of time periods where there's no demand, but when it comes in, it might be a big burst. So when you have demand that's very sparse or very consolidated into bursts, then there's different methods you can do. There's also what you'll see is the inventory model, and maybe this is what Prashant was getting at, is you use the inventory model that matches your demand distribution. So if demand is deterministic, there's no variability, then we have one set of models. If it's variable, and it's variable, but it's deterministic, I mean, I know where it's going to change, I might use a different model. And so if it's a short period of time, I have a different set of models. So what you'll see is different inventory models are used based on the assumptions of the demand. Hopefully that makes sense. It'll make more sense if you take SC0x. We spend probably 3 weeks covering these different models.
Yeah. And perhaps a follow-up to that is, are we also using different distributions then? So for instance, Prashant also asks if we're going to use, I think he had Poisson and,
so
negative binomial.
So the lion's share, to be honest, in most systems assume normal. Small, then we'll obviously cover normal. We'll cover Poisson. I won't go into log normal. I'll hint at it, and there's different ways you can do it. I won't go into any binomial, negative binomial. You can go truncated normals. There's the inventory modeling pool is very deep. And so there's a lot of depth you can go. We won't go into multi-echelon inventory. We touch upon that in later courses. I think we touch it a little bit in SC2X. That's a more advanced topic. But the concepts are all the same. And hopefully the concepts of it, if you change the distribution, all that matters is how you figure out that probability of stocking out. That's the only thing that changes. Whether it's a normal, whether it's triangle, whether it's Poisson, All you're doing is it's a different method you plug in to figure out your probability of stocking out or your expected number of units short. That's all that it is. And then it just gets mathematical. But we cover most of that. All right. Then in SC2X, it's all, if you like mixed integer linear programming, you will love SC2X. It's all about design. SC2X is supply chain design. And there are three elements of the flows. You have the physical flow, the information flow, and the financial flow. And so the first half of the course is based on the physical flow. And that's network design, network flow analysis, channel design. How does product get from origin to final consumption? And so that includes where should I set up facilities? How many should it be? Which facilities should serve which endpoints? How do you flow things through? And it's all a huge mixed integer linear program. And you'll get more skilled on the different techniques because we go a little deeper than we did in SC0X. In fact, we actually explained some things in Excel doing that because SC2X was the second course I created. And so you'll probably be able to do it even easier if you've gotten comfortable with SAS or Ample, to be honest. But I show things in Excel because I blow up the constraint matrix because to me, that's how I learned. I learned doing it by hand. And so hopefully when we go into the details, looking at it in the constraint matrix, that'll make more sense to you. But we go into a lot of depth there in mixed engineering programming for aggregate scheduling, production planning, and a lot of different things. We also will go into finance and other areas, but they're not as model-based. And SC2X is kind of like the keystone course. Everything prior to that, 0 and 1, is all very mathematical, modelly, halfway through, and then we start getting more qualitative. So we go into the financial aspects, we go into procurement, and some other different things. In SC3X, we get in, and the big focus there is we now introduce exogenous factors. Say, okay, here's what the model says, but you've got these state regulations, or you've got a border, or you've got uncertainty. This is coming in, so a disruption. So how does the real world influence your models? So we'll introduce system dynamics, which is a mathematical simulation technique that I thought about putting into 0, but I think it belonged closer to the application. And so system dynamics is an interesting technique. It helps you understand the dynamics of a system, how different entities interact with each other, because that's what a supply chain is. We'll get into risk contracts. So if I have a supplier and say a manufacturer and a retailer, and how do they share the risk between how much they order? And we'll leverage some of the stuff we did in SC1X called the news vendor problem. And that will leverage things that you just learned in SC0X, which is probability distributions and unconstrained optimization. SC4X is now we're going to large scale things. And so the big learning from SC4X is how to do this analysis in practice. So instead of doing things just in a spreadsheet, you've got to use SQL. So you have a relational database. So we spend a lot of time understanding why you use relational databases, how to use a relational database. Because if you get in real life and in real research projects, you'll have millions of records that even though Excel can handle a lot, it doesn't make sense. There's other tools. And so MySQL, we use that to help you understand how you can handle large scale data. And then also machine learning, which is kind of, again, something we thought about teaching in 0X, but I think it really hits home when you see the problem of having massive data sets. So kind of in the very last course, we introduced some new math again. But prior to that, you're really using only the stuff that you've learned so far. So SC0X is really setting you up and providing you a foundation for all the SCX courses. Think of it as a toolbox. So now you've got all these tools, and you will use all of them throughout your course, not all at the same time, but I think it's very useful for you to know what's in your toolbox. So when you see a problem, you say, that looks like an optimization problem, or that might be best solved by simulation. Because what you'll see in practice and in research, the same problem can be approached by many different techniques. And so you've got to pick the one that you're comfortable with and you think gives you the best answer. That make sense?
Absolutely. Thank you, Chris. So we have a couple of questions from our learners that are getting more thumbs up, and they all circle around how do we use these methods in practice. So Mo, for example, asks, many concepts have been had covered during SC0x, I can't imagine how to use these models and methods in real-life supply chains. The other, Sahil is asking that this was a great course with lots of problems, with lots of practical problems, whether the other courses have similar practical components, are they practically related? And the third one that I just saw is we've gained a good knowledge on SC0x. My question here is how to get the most benefit possible of implementing some of these concepts. So for me, there are two components.
Okay.
One is how does that relate to further courses, because we are setting the stage for further courses. I think you have covered that already. The other question is, how does that help me in practice?
Yeah. And so I'm going to do some examples here, but it depends where you are. I mean, to be honest, if you're in a planning group, which a lot of our graduates go into planning groups, whether you're doing demand planning, inventory planning, procurement, where you're doing more strategic kind of analysis, you will use a lot of these techniques. And if you're in any demand planning, you will use regression. You will use some kind of stochastic modeling, without a doubt. If you are in procurement, you're using optimization. It might be hidden because you might be using a system like Ariba or other systems that are out there, but underlying, you'll know that there's an optimization model. And that's the big thing. What a lot of students complain about sometimes is like, why do I need to learn this math if I've got software that can do it for me? There's just so many cases where people think software is magic. And it has limitations of what you can and can't do. And so I think it's exceptionally important, and that's my hallmark here, is to make sure you understand the fundamentals. We're not going to teach you necessarily how to use each software tool. We do some in recitations, but all of them sit on the same fundamentals. And as long as you know those fundamentals, in my opinion, it's easier to use one or the other, and you understand the strengths, the weaknesses, the limitations of each of these methodologies. So that's why we always go to fundamentals. If you want to learn just how to use a certain software, go to YouTube and my gosh, I use that if I want to brush up on something, find a video of someone entering something into SAS or into SAP or into CPlex, and you'll learn that, but it's dangerous because you need to understand what things you're standing on, what assumptions you're making when you use that software.
Okay, so to add some of the practicability of our methods, we have prepared a couple of problems from practice. And I'd suggest we go just step by step through them.
So I picked these.
Right.
We don't. Okay.
So, but what we want to do is we want to present the problem to you and then ask you with a quick poll of how you want to solve them. So dip into the tool belt and think about, well, how would I approach that? Which method do you think is most appropriate to solve the problem? And I will open that first poll for the first problem. And you can, while Chris is presenting it, you can think about, well, how I would tackle that.
Perfect. All right. So I picked these problems because these are actually mainly based on work that I've done with companies here while at MIT. Some resulted in capstone or thesis projects, but every one of them has a company sponsor. So the first one, you want me to just do it?
Sorry,
there you go. You got it? Okay. Is with a company called C.H. Robinson. It's level of service, LOS versus price. And so you can read it, but let me just paraphrase while you're reading along. The situation is that C.H. Robinson is actually the country's, probably the world's largest freight brokerage company. A brokerage company is simply a middleman or a third party between a shipper, someone who has goods to move, and a carrier, someone with a truck, right? And so they broker the relationship. Sometimes they're called a 3PL or a third-party logistics provider. I'll just use brokerage. And one of the lines of business for CHR is that they will completely outsource the management of the transportation department. And so in this role, they will select which truckload carriers to use, and they will actually operate that on a daily basis. When they make the selection of which carrier to use, they typically make it some kind of trade-off. Whenever you hear trade-off, you think optimization, right? Between price that they have to pay the carrier and the level of service they're going to provide. And so level of service is one of those squishy things that means different things to different people. But in this case, it meant a combination of on-time delivery, on-time pickup, the transit time, the acceptance ratio, the damage ratio, all these kind of things. Acceptance ratio in truckload trucking is this. If I offer a load to a carrier and they reject it, then that dings against them. And so I look at that percentage that they accept. Contracts in the US are a little weird. So acceptance ratios can be like 90%. But if it starts dipping low, then that's a problem, because then the shipper, or the broker in this case, has to go and find another carrier. So you try to keep the acceptance ratio very high. You want a carrier to accept all the loads offered to them. And remember, I don't think I talk about truckload carriers. I might a little bit when I do the transportation approximations. Yes. Truckload carriers, as opposed to less than truckload, right, or parcel, go from point to point. So a truckload carrier will pick up a load from this manufacturing plant and go deliver it straight to a customer's DC, or distribution center. So they go point to point like a taxi cab, as opposed to something that picks up a lot of smaller loads, consolidates, and delivers that way. That's more like a bus. So we're focused on truckload trucking. So CHR does this for a bunch of companies, and they came with a question, and they said, basically, does level of service have any relation to the cost? So the amount that I pay, because it seems an intuitive thing. If you pay more, you get more. And so that's the question. And say, should we pay more for better service? Do we get better service if we pay more? What drives that level of service? Is there something that we can do to improve the level of service that carriers provide us, or reduces the cost? So that's the question. So how are we doing?
Ooh, we have about 20 answers. People are still digesting.
Oh, come on. You guys got to make decisions.
But I think some of them have an initial intuition that maybe it is a constrained optimization problem. So you set up an LP or a mixed engine LP. Or that it may be more something for regression, and think about how different factors that we were talking about influence the price.
So unfortunately, you guys missed the one. Only 11% is saying the biggest thing, large-scale data analysis. Because we're doing a project now, this is ongoing. We've had a series of projects with CHR. We're doing one right now looking specifically at the impact of lead time and level of service. And it's massive amounts of records. And so when you, and the interesting thing, this will be in practice, you'll get data from multiple sources, merging that data, cleaning the data, explaining what the heck they meant with different fields. That's a big time job. I have 2 students working on this now, and it's taken them weeks to try to understand and get the clean data set. So before you can do any of the analysis that we've done in this course, you got to make sure the data set's clean, pristine, and you understand everything that's there. The way we're handling this is mainly going to be regression. I threw a red herring, if you know what that means, when I talk about optimization. But really what you're doing is you're saying, okay, my dependent variable here was cost per load, and my independent variables were the origin region, the destination region, the distance, and then possibly level of service. We also did a series of models using regression, but it's a different type of regression that looked at the probability that a carrier accepted a load or not, 0, 1. It's called the binary logit model. It's a little more advanced, but it's a regression. It's the same thing. I have a dependent variable. It just happens to be a 0 or a 1. We talked about that, right? So I can't use just ordinary least squares. It's a slightly different technique. And what factors influenced that a carrier would accept it or not? So we tried to quantify that, and then we used hypothesis testing to see if I have a low-cost carrier versus a high-cost carriers, is there a substantial difference in their level of service? The punchline is, and this was a surprise to everyone, but we've repeated this results in a lot of different examples, is that level of service and price are not correlated. So paying more doesn't necessarily mean you're going to get better service in truckload trucking. What we found, the interesting insight, and this is why research is so much fun, we found that some of the best performing carriers were the cheapest ones. And to understand why that is, you have to take SC0x, but I'll give you the hint. They tended to be smaller regional-faced carriers that operated within a certain region instead of what's known as nationals that are operating everywhere. And so what we found is some of these smaller regional carriers offered better service because they were C.H. Robinson, or the shipper, was a bigger piece of their business, and they tended to operate on a known set smaller area of the network, and they were working with a very large customer. The nationals, they have to operate everywhere, so they tend to be more expensive because they have to cover a lot of holes where there isn't a lot of traffic, and their level of service is not as great. So it was kind of an interesting analysis, and we've done this in a bunch of different ways to understand different factors that influence the cost. You also have to build more of a geographic or a spatial model to understand that if I leave from origin A to B, that's not going to be the same cost as if I leave from B and go to A. And that's something we'll talk about in SC2X when we talk about network design, because what we found is, and this is pretty well known in the industry, it's not symmetric. The cost of going from, I always use this example in the United States, Chicago to Miami is not the same as going from Miami to Chicago. And we'll talk much more about that in SC1X.
Very interesting result you have there. So you've related that problem to SC1X and SC2X for transportation network design. Is there also a course that talks about how to manage big data? Do we touch that at
we
some
do a little
point?
bit. SC4X, we cover it, but we do enough to make sure you understand how the big systems and supply chains work. There are some great data analysis courses on edX. A new MicroMasters is coming out from our IDSS that is going to be specifically on a large-scale data analysis. So there are other very specialized courses where you can go much deeper into the math for these, but we cover some of this in SC4X. Yes.
Okay. So
yep.
I think that is what was one question that came up with big
sure.
data, because that's a hip topic and everybody thinks about it, and students probably want to know more. So we're doing a little bit about that.
Yeah, we cover that in. So here's the thing: all the techniques you've learned when we do data characterization, that's big data analytics. You just have to be able to do it outside of Excel. So the concepts are the same. Now machine learning is a different animal, and so that's different because that's where, you know, when we do regression, hopefully we made the point that correlation does not mean causation, but that you want a story. I kind of stress this. So we did something where we did, I think I did it truckload pricing, right? Cost is a function of distance, all these other things. And so they had to make sense. I couldn't make it my independent variable be, the color of the trailer, or the number, the last digit on the license plate. Because let's say there's a correlation there. What am I going to do with that? Machine learning is just the opposite. They don't care. You just find correlations. You're hunting for correlations, and there's a lot of great techniques, and it uncovers things, whether you're supervised or unsupervised. So SC4X is a good course that'll cover some of this, and it's a nice launch pad for you if you want to go deep. Because again, just like inventory theory, machine learning is a deep pool, and the math gets really tricky, really deep, really fast.
Yeah, and lots of different ways to do it too, right? So there's so many different methods to apply machine learning. It's such a big pool. So.
Yeah, but you can, so supervised machine learning, regression is supervised machine learning.
Yeah.
So, a lot of it's just the names, the labels put on, but it is a great field, and it's really expanding what we can do.
Shall we move to the second problem? I will open up a new poll, and while you're presenting, we'll see how students think about that.
So this is a problem we did with Starbucks about 2 years back, and this is based on a thesis by Vicky and Cecil, Efficient Supply Chain Design for Highly Perishable Food. So this is based with Starbucks, and hopefully everyone's heard of Starbucks. I think they're everywhere. They're in Italy now. Quick service restaurant. They mainly service coffee. I mean, they're a coffee shop, but they do other things. But they replenish each store daily from a regional DC, an RDC, using a third-party distribution company, usually between like 10 o'clock at night and 4 in the morning when it's closed. But in addition to selling coffee, they've started selling fresh food, not just stuff that's frozen, but actually freshly produced each day, because they're finding they want to get more into the afternoon. They want to have like lunch meals and not just be a morning breakfast place. And so the fresh foods are made by a third party. They don't do it themselves. They have different companies located around their network, and they make these sandwiches. These stores will send an order in the afternoon. It gets assembled by, I think, like 8 o'clock at night. By midnight, it's ready to be distributed, and it has to get to the stores on a daily basis. And so right now, the fresh food component is very small compared to the other products, right? But the question is, the Starbucks had is, how do I flow this fresh food products to its stores? Should I have the supplier, the company that's making these sandwiches and assembling them, should they send it straight from its plant to the Starbucks DC? Then it gets combined with the other things getting distributed. Should the supplier send it directly to each of the stores? Should they consider, when do they consider one distribution channel versus another? So this is the question that Starbucks had. How do I get my fresh food to the stores daily as efficiently as possible? So that's the question.
That's the question, and people are starting to think about it. I think we give them perhaps 1 or 2 seconds, 16 answers and counting, hopefully counting.
And so one of the skills hopefully you'll learn by doing this is, yeah, you have the tools, and I am glad you guys asked the questions, when to use which tool. Because that's part of the thing, is first identifying what the problem is. The second is adding, how should I approach the problem? The third is, how do I actually solve it? What data do I need? What techniques do I need? So it's kind of steps, identifying what is the problem, what class of problem is it, and then what do I need to actually solve it? Because a lot of times you'll identify something and say, oh, that's an optimization problem, but the data doesn't support it. You don't have the data to be able to do that, so you've got to find a different approach. And that's why I covered some of those approximation techniques early on in the first half of the course.
So about 33 answers right now. Constraint optimization is in the lead. So they want to set up a network design problem, I would say. And then there is a second group that is perhaps more concerned about the size of the problem. So they are thinking about algorithms and approximations here, and simulations, perhaps.
Yeah, so they what we developed was a total cost model of how much time it takes for product to flow, and if it went on one vehicle versus another. And what they found is it's really a function of how much is flowing through the system. So currently, it makes sense if they were going to deliver straight from that food production plant to each of the stores themselves, they'd have to do a multi-stop. They'd have to go to multiple stores, like 15 different stores, to have enough to fill a truck to justify that route. So initially, it probably made sense to go deliver all the fresh food to the Starbucks DC, which adds time, right? And then it gets added on to the other standard deliveries. What that does is that almost adds a day, right? And so what we found out, what we could do, you could try to see, can we shift the time when they start? Do they start at 8 and finish by midnight? Can they start at, say, 4 and finish by 8? And then we can combine them with that same day. So the challenge they found, once they understood the trade-offs, was that if I piggyback off the existing deliveries coming in for all the other product, I lose a day. If I go directly, I gain a day, but it's more expensive. And so they did do a constrained optimization, and they actually used some approximations. And so, because what are we doing here? It's the same approximations that you did. So they're going to a number of stores in a set area of a set density. In Boston is where we did the analysis. So you don't know exactly which routing they're going to use, so you don't use an exact algorithm, you use an approximation. So if I know I have to deliver to 20 stores within this 10-mile area, I know the density, I can figure out the expected local distance, I can figure that cost. So what we did is we used an approximation of the local delivery cost to make that trade-off of, do I go through existing channel or do I do a direct fresh channel? And so they found that the current situation for the sample, the pilot that we looked at, it made sense to piggyback. However, as the volume increased, there's a tipping point when it makes sense to go direct to stores with the fresh food. And so we're able to identify how to find that tipping point and when that would happen, because that helps planners, right? I can start saying, okay, my forecasters say, you know what, forecast, again, a technique for regression, I'm seeing demand increase like this, so therefore I can plan 18 months out, I'm probably going to need to have a different distribution model, maybe go direct. So what this this thesis was able to do was help them, one, quantify very quickly what parameters are driving the decision of whether to go direct or to piggyback off of existing, and then two, what signs to look for to know when you want to make a switch. I'm trying to think what else we did there. I think that was mainly, it was a fun project. It was really nice. And we developed, it was all in Excel. This was totally in Excel. And we handed the project, the spreadsheet off to them where they can make this decision very quickly, just changing some parameters. The other thing we can do is we can play with this and say, okay, what if situations change? What if the density changes? What if the value of the products change? Because we also looked at the holding cost of having too much inventory. Because one thing you could do is deliver every third day, but then you've got inventory hanging around as opposed to delivering every day. But the trade-off is if I deliver more frequently, I have less perishable, less items getting spoiled. I don't have to carry as much inventory, but I'm paying more that frequent delivery. As the opposite, I deliver less frequent, right? So my transportation costs go down, but my inventory holding cost goes up, and my waste cost might go up because I might have some things that, you know, you don't want to buy the sandwich that's 4 days old. So you have waste. So there's a trade-off there. And we're able to capture those costs and then use an optimization model to figure out the best path.
So a lot of techniques that we taught in SC0x used, and we will be doing that in SC1x and SC2x more detailed.
Yes.
And dig more into network design problems and how we can actually tackle these problems, right?
Right.
Want to go to the third problem?
Yeah, let's go to the third.
And while you're talking, I will again open up the polls to see where students are going with it.
So this seems to be the same problem, but it's a little different. This is Walmart, again, the world's largest retailer. We've done projects with them for years. They're a great company. They've innovated in the transportation logistics space for decades. So they're a large discount retailer. And originally they were dry goods. They got into grocery in the late 90s, and they are now certainly the United States' largest grocer. They might be the world's, but they're certainly the United States by a large margin. And so the difference between just being a discounter, where you can put things in dry van trucks, you don't have to worry about a shirt spoiling. For grocery, you have to deliver different product temperatures. And so they're generally three: ambient, which is just room temperature, dry van. But then there's refrigerated, and then there's frozen, and there's even some in between. So you don't want to have ice cream delivered in a refrigerated truck, and you don't want to have, say, grapes or other fruit delivered in a frozen truck, right? It'll damage the product. So you have these three different types, and traditionally they would replenish a full truckload of a specific temperature zone to a store. So they're ordering, their dry van stuff, their regular dry goods stuff. They have an ambient truck, and they'd have all stuff that can be kept at room temperature. They deliver that. They have a full refrigerated truck, and so all the milk, all the dairy, all that stuff gets delivered in one. And so it might be that that refrigerated truck would have to go to 2 stores to unload. Well, what's happened is they've started a new format of smaller stores in urban areas, and it was turning out that they'd have to do multiple stops. It wasn't just 1 or 2 to take care of a full truck. It would be 3, 4, 5. And as you start doing that, you start running out of time in the day. And so it starts becoming uneconomical. And so what they've started looking at is multi-temperature trucks. So think of a truck with zones, and they can actually move the sliders. One can be frozen, then refrigerated, then ambient, right? And so the question is, should I use these trucks? They cost a little more. And then the question is, if I have these, how should I use them? Should I make it so that I use the classic trade-off is, should I have single zone trucks delivered to multiple stores, or should I try to have a multi-zoned truck delivered to single stores, or a multi-zone truck delivering to multiple stores? And so trying to understand which stores get serviced by which type of vehicle, and then how much space do you allocate for that? That's the question that Walmart wanted answered.
That's interesting. I have never thought about it. I'm not a transportation person. I have never thought about trucks with multiple compartments. Are they more expensive if
they're a little bit more, and they take up some space because you're taking up space by having these dividers. And anything, and you learn this at SC1x, risk pooling, right? So if I take one big zone, I can store more stuff in one big zone than in 3 zones that sum up to the same area, because I'll have gaps in each. But yeah, it is a little more expensive, and because the other thing is you're paying for the generator unit even for that ambient. stuff that's there, because it takes a generator, a refrigerator unit.
So our students have about 30 replies here, thinking again, constraint optimization, algorithms and approximations. It's coming in some regression now, and simulation again.
Yeah, we thought about simulation. That was our first go-to, because we could trade different policies, like every store delivered every day. What would that do? Every store and then we'd have to figure out a rule or an algorithm for when to use multi-stop. But we could test different policies. We chose not to, because and we went with the constrained optimization approach for this, actually. And so it was a mixed integer linear program here, where the objective function was the total cost. And the total cost, you can think of it as for each pallet being delivered. So you look at every store had a fixed demand. So think of your constraints. Store A had certain demand, and we did weekly based buckets, number of pallets frozen, number of pallets refrigerated, number of pallets ambient for each store. You had to meet that. And then the question is, my decision variable was the number of pallets assigned to each type of truck. And so we minimized the total cost, which is the transport cost, the stoppage cost, and the holding cost. And you'll learn in SC0x what holding cost is. But essentially, the idea is, if I buy a week's worth of stuff and I keep it, and I buy it all at once and it's there, versus I buy a day's worth of stuff every day, right? You can see there are different inventory levels. So the holding cost is the cost of holding that inventory for a period of time. And what you'll learn is that it's not the total purchase cost. You have to look at what the hurdle rate is, the H or the R that we call it, which is what your cost of capital is. So it might be like 20%. And so as you order less frequently, your holding cost, or your inventory holding cost, goes up, right? As I order more frequently, my holding cost goes down, but my transportation cost goes up. And so you have that trade-off of transportation versus inventory. And so what we did is really made a trade-off between the different modes. And because some stores, if they had a demand that was high enough, then it justified a full truckload, right? And so this is the model that we used, the mixed integer linear program, that determined how to replenish each of the stores. You could have easily done this also in a simulation. It'd be a cool way to do that as well, where you're testing different policies, but it would not tell you which trucks to use. It will tell you, it'll say, given this policy, here's what you will get.
That would actually have been my question. How do you determine, because there are a lot of students asking about simulation. Why not use simulation for this project, or also for the second problem with Starbucks? Why don't you use a simulation? Why do you opt for an optimization?
You can. I think we didn't. One thing is that the companies wanted answers, and so it was less of a policy situation. And in fact, for what you see for both of those situations in practice, what a lot of companies will do is you use both of the tools, right? So you use a simulation, and you do an optimization to find an optimal solution. Then you simulate how things will look, because in optimization, as you saw, the demand is deterministic, right? Everything is fixed. And so what you can do is two things, and we'll do this in SC0x. I can run the optimization multiple times, where I take a random sample of my input variables. And so we do this for network design, and you can see, so you run the model multiple times based on essentially a Monte Carlo pull of the data. The other is you have a solution, then you change the demand and see how well does it perform. And you can play with both of those. So we thought about that. And if I had a follow-on, maybe I would consider that. But for the simulation, you would have to have an optimization embedded within it. Because what the simulation is, what are you simulating? And you'd be simulating demand, right? So if demand changed, you would need to say, what you're doing is you're saying, okay, demand for store A is now 10 instead of 20, right? So you need to have an algorithm or heuristic that says, okay, based on these demands, I would use this truck, this truck, this truck. So the simulation is really just simulating the demand. You'd still need a piece in there that is making a decision of what loads to assign to what trucks to what stores.
Also solved in Excel, this problem in Walmart?
No, it fed into a, gosh, what did he use? We had a PhD student help with this, and he coded it, I want to say Cplex. He used Cplex for the optimization. in Excel, we use that as the front, and it called the other thing.
Okay.
What we're finding now is more and in fact, we're doing this here in SCX, SCM, the courses here. We're teaching Python now. So if you want to go to grad school, learn Python before you come. You get any edX course. There's great Python edX courses. We're finding that for the large data, Python is the language to go to. It's easy to use, and a lot of libraries where you can do a lot of these different things. So if you have free time, it's open source. Learn Python. We're finding it's. I wish I stopped coding using C in the early '90s. So learning new languages, but I recommend it if you haven't done it already.
So we have
How are we doing on time?
4 minutes left. So I would suggest we tackle some of the questions that are more general, if that's okay with you.
Yep.
So perhaps we talk shortly about the final exam. Do you want to do that?
No, you can.
I can. Okay. So final exam is what you have seen in the midterm. The midterm is essentially the same as and reflects what we are going to do in the final. We're going to have 3 problem sets plus checkbox questions. And the entire content that we served you with from week 1 to 4 and 7 to 10 will be covered. So we are going to ask questions about all of that content to see your proficiency. So it can also be, just to be very specific, can also be the content of week 1 through week 4.
Yes, it's not just the second half of the course.
Yes. But other than that, you can expect exactly the same. It's going to be released today.
No, tomorrow.
Sorry, tomorrow.
Today's Tuesday, right?
Today's
Tomorrow.
Tuesday. Tomorrow it's going to be released tomorrow. Yes, and we leave it open for 7 days until December 5th. It will be a timed exam again, so you will have 4 hours once you open it. So you decide when you want to take it, but once you open it, the clock is running and you have 4 hours. And remember that if you're taking it on Wednesday in our morning, so right before the deadline, you need to have 4 hours before the deadline, because when the deadline hits at December 5th at 1500 UTC, we will close the exam.
Yeah.
So you need to account for that with the 4 hours. Other than that, it's an open book exam, so you can use all the tools that you developed. You can use the videos. You can use the practice problems if that helps, and you have time to revisit them. You can take a look at your notes. So it's open, but it's all your work. So you're not allowed to coordinate. You're not allowed to work in groups. That is absolutely forbidden. I think that should be covering it.
What other questions do we have?
So we have a couple of questions about the course setup.
Okay.
So is it mandatory to take the courses in sequence, SC1X, SC2?
No, it's recommended because if you take, say, SC2X without taking 0X, you might be wondering what a mixed integer linear program is. If you're not brushed up on your mathematical dexterity with algebra, you might get tripped up on SC1X. Hypothesis testing is used a little later. So, no, you can take them out of sequence. We recommend taking them in sequence, but you guys have busy lives. Sometimes people want to take 2 courses at once. You want to start. So we try to set expectations. And you can always go to the key concept document for the whole course and kind of go through and say, okay, what's going to be covered in this course? Am I going to be out of my depth? So we recommend it, but we don't enforce it.
All right.
Anything else?
No, I think we're set. We have a couple of questions left, but time is running out. I think we've covered a lot today. Thank you very much for taking the time, Chris. That was really interesting to see all these programs and how we can actually use the tools.
I encourage you to take SC1X. To me, it was the first course. And it's SC1X and 2X are my favorite courses because they really tie together things, and you'll use them a lot.
And SC1X is coming up, right?
Yes, it is. It's starting in first week of January.
Yeah, so you can sign up and think about and see how we think about inventory management, about forecasting, all that kind of stuff.
Yeah, give it a try. Even if you don't want to do verified at first, just go for the first couple of weeks. We'll start talking about demand forecasting. You'll start seeing how these models and everything you did, the pain you went through to learn these models, how they're actually used.
So thank you very much, guys. The video will be up on our channel if you want to revisit it. And I wish you all the best for the final exam.
Good luck, guys.
See you soon. Bye.
Take care.